Let's talk about the single most important invention you've probably never even thought about. It's a tiny, almost invisible switch that quite literally runs our entire modern world. It's called the MOSFET, and honestly, it's the unsung hero of the last 50 years. To get a sense of its impact, let's rewind a bit. Back in 1949, you have the ENIAC computer. We're talking a room-sized beast, filled with glowing vacuum tubes and clicking relays. It took that machine a full 70 hours to calculate pi to just the first 2,000 digits. I mean, for its time, that was absolutely revolutionary. Okay, now fast forward to today. That smartphone you're holding in your hand? It can do that exact same calculation in less than half a second. From 70 hours to half a second. That is a mind-boggling leap in computing power. So, what happened in between? What could possibly account for that kind of jump? Well, the answer isn't some huge, complicated engine. Nope, it's a switch. A switch so small you can't see it. And there are billions, literally billions of them, humming away inside every single piece of modern electronics you own. And that amazing little switch is called a MOSFET. It's a very specific kind of transistor. And it's no exaggeration to say it is the fundamental building block of our digital world. Your laptop, your TV, your car, your watch, they all run on these things. They are everywhere. Right, so Metal-Oxide-Semiconductor field effect transistor. Yeah, that's a mouthful, I know. So we're just going to call it a MOSFET. But you don't need to remember the name. Just remember this one huge idea. It's a perfect electronic switch that you control with voltage. That one simple fact is what changed absolutely everything. And to really get a handle on this, there's a fantastic analogy that everybody uses because, well, it just works perfectly. Think of a MOSFET as a simple water tap. So in our analogy, the handle you turn is called the gate. That's your control. The water flowing through the pipe is your electric current. It flows from an inlet, which we call the source, to an outlet, which we call the drain. But here's the secret sauce. It takes almost no effort at all to turn the handle, right? But with that tiny bit of effort, you can control a huge, powerful flow of water. Tiny effort, massive control. That's the magic of the MOS. So how does this little electronic water tap actually work? I mean, what makes it so perfect for the job? To get that, we've got to pop the hood and look at how it's built. The name Metal-Oxide-Semiconductor isn't just a random bunch of words. It literally describes its structure. It's a sandwich. You've got the metal gate on top, that's our handle. Then there's this incredibly thin layer of oxide, which is basically glass, and it acts as an insulator. And below that is the semiconductor base, which is usually silicon. That tiny oxide layer is the whole key. It completely isolates the gate, which means you need almost zero power to turn the handle. Okay, but wait a second. If the gate is insulated, how in the world does applying a voltage to it make current flow? There's no physical connection. Well, the magic is right there in the name. It's a field effect. Here's how it goes. When you apply a positive voltage to that metal gate, it creates this invisible electric field that punches right through that thin oxide layer. This field acts like a magnet. It reaches down into the semiconductor and starts pulling all the negatively charged electrons up towards the surface. Once enough electrons gather there, poof, they form a temporary conductive bridge, a channel, connecting the source and the drain. And just like that, the tap is open and current flows. Take the voltage away, the field collapses, the bridge vanishes, and the switch is instantly off. It's brilliant. So this really elegant on-off mechanism gives us a few basic rules and a couple of different flavors of MOSFETs. You see, they're not all created equal. They're designed for different jobs, and it mostly comes down to what their default state is. Are they normally on or normally off? Now, the one you'll find pretty much everywhere is called enhancement mode. Just think of it as a button you have to push to turn something on. It's normally off, and you apply a voltage to enhance it and create that channel to turn it on. The other type, which is way less common, is called depletion mode. It's the opposite. It's normally on because it has a channel built in, and you apply a voltage to deplete that channel and turn the switch off. And depending on the voltage, a MOSFET can operate in 3 different ways. Let's go back to the water tap. In cutoff, it's completely off. The tap is shut, no water is flowing. In the linear region, it's like you've opened the tap just a little bit, letting you precisely control the flow. But in saturation, the tap is cranked wide open, letting the maximum possible current through. Now, for the digital world of ones and zeros, computers are just slamming these switches back and forth between cutoff and saturation, fully off and fully on millions of times a second. So we have this tiny, incredibly efficient and elegant switch. Now, let's look at how being able to make this thing small didn't just improve electronics, It completely reinvented the entire world. So why did the MOSFET totally take over? Well, it comes down to three game-changing advantages. First, because of that insulating layer, it takes almost no energy to flip the switch. It's incredibly power efficient. Second, it is blazing fast. And third, and this is the big one, it scales. You can shrink it down and down and down again to almost unbelievable sizes, which lets us pack billions of them onto a single tiny chip. And that scalability led to the greatest breakthrough of all, CMOS, which stands for complementary MOS. The genius of this design is that it pairs two opposite types of MOSFETs together. So when the circuit is just sitting there, either fully on or fully off, one of the transistors is always blocking the current. This means the whole pair uses virtually zero power, except for the tiny instant they are actively switching. This is the technology that makes battery-powered devices, like your phone, even possible. So how many of these tiny switches are we really talking about here? Well, the main chip in the phone you might be watching this on, it doesn't have thousands of them. It doesn't even have millions. It has over 50 billion MOSFETs. That is not a typo. 50 billion switches, all opening and closing billions of times every single second. It's just staggering. This is it. This is the engine. This one tiny switch is what took us from a 70-hour calculation to one that takes half a second. It has driven the entire digital revolution. So as we find ways to shrink it even further, to pack hundreds of billions or maybe even trillions of them onto a single chip, you have to wonder, what incredible leap is